So we're looking at confidence intervals for slope. So suppose that a researcher was studying the relationship between the outdoor temperature in degrees Celsius, which will be our X, and the depth of a woodpecker's nest in centimeters, which is the Y. Now, woodpeckers, do you know what they do?
Peck wood.
They peck wood. And so depth meaning how deep into the tree they go. That's the depth. Okay, based on a sample of 12 nests, a regression analysis was conducted, and the results are shown below. Does this give evidence that woodpeckers dig deeper when it's colder outside? So we are trying to answer this question. Do woodpeckers dig deeper when it's colder outside? You may assume the conditions have been met. So, what's our least squares regression line?
Y equals
Let's not use Y, let's use words.
So depth.
woodpecker's nest depth.
Depth of nest, yep, in what unit? Centimeters is equal to, what is the y-intercept from this printout?
Negative
Nope, that is not the y-intercept. 20.1251. It's always the constant. That is the y-intercept. Plus, it's a plus bx, which is the same as mx plus b, it's just written backwards. So plus, what is the slope? Negative, so plus a negative 0.34504 times, what does the x value represent?
Outdoor temperature.
Outdoor temperature. So I'm just going to put temperature in degrees Celsius. So what happens? So let's just think of what does the slope mean in the context of the question. For every one, remember the slope, negative 0.345 over 1 is rise over run. So run is referring to the x. So for every 1 increase in degrees Celsius temperature, for every 1 degree increase in temperature, the depth of the nest does what? Goes down, yep, decreases, goes down by how much? Yep, 0.345. And that's going to be centimeters. Down is taking care of the negative. So, let's see, what would be the null hypothesis here? No linear association between what? Temperature and depth of nest, yep. And the alternative hypothesis is that there is a linear relationship. There is a linear association. So again, in symbols, the null hypothesis is beta, the slope is 0, and there is a linear association. Now, do we want to say positive or negative? Okay, so we want to say there is a negative linear association. In other words, we're saying beta is less than 0, the slope is less than 0. So we want to just do let's just do a quick t-test, a linear regression t-test. So we're just going to do a linear regression t-test, and we're going to do this the same way we did in problem 29 that we just went over. Yep, t is less than, we're going to write down our formula for t, b minus beta over s sub b.
Isn't it the first thing you write, the probability that beta is less than that, and then
Well, you can just, we can just write it like this. You could start with, here Mitchell was referring to this, the probability that b, our observed slope, is less than the negative 0.345. That is that's the slope we're looking at. What's the probability that we get a slope that small or smaller, assuming that there's no association, no linear association? So we're going to find the test statistic for that. So from up here, from this information up here, this is my B. What's my beta? 0 from my hypothesis. And S sub B, the standard deviation, standard error of the slope, it's right there. SE coefficient, SE standard error, standard deviation, it's that, 0.06. So I'm just going to plug in, that's a probability that T is less than negative 0.345 minus 0 divided by 0.06008. So I get that my P, my T test statistic is what?
Negative 5.7.
Negative 5.74. In fact, wasn't it right here? See that? Isn't that the same that we got? There it is, test statistic. And what's the p-value that goes with that? 0. The p-value is approximately 0. It's right there in the computer printout. If you wanted to do that on your calculator, you'd go second distribution, TCDF. Your lower bound, since we're doing less than that, negative 5.74, our lower bound is negative infinity. Our upper bound is negative 5.74. And what were our degrees of freedom?
It'd be 12 minus 2.
12 minus 2. So the degrees that we should list somewhere in here that the degrees of freedom is 12 minus 2 or 10. So 10 degrees of freedom. And that this gives us, it says 9.38 times 10 to the negative 5th. That's pretty much 0. So, and notice they just cut off after 3 decimal places. So, all right. So is there evidence of that woodpeckers dig deeper when it's colder outside? Yes. Okay. So suppose, now we're going to look at a little bit different. Suppose that the previous research suggested that for every 1 degree Celsius, increase of 1 degree Celsius, the depth of a nest decreased by 1/3 of a centimeter. Does this new study disagree with previous research? State the hypotheses, the p-value, and the conclusion. So this is an example we talked about, well, it was mentioned in the last note, so I want to go refer you back to the last notes. It says, right here, this is on page 197, this little note, your calculator and most statistics software only test for beta equals 0. So if you're testing for something else, you need to calculate T by hand. That happens to be the case here, but didn't we just calculate T by hand in the previous, we calculated T by hand here, didn't we? Well, we're just going to assume that that's all we know. Okay? So we're going to use this same computer printout, this same data that we had here. But now we're going to have a new set of hypotheses. We are going to compare our research to the previous research. So what this does is it changes our null and our alternative hypothesis. So instead of saying beta equals 0, we are testing this against the old research of 1/3 of a centimeter. So beta is negative 1/3, which is the same as negative 0.3 repeating. Okay, that's the decimal. And our alternative hypothesis would be that it is not equal to that. So this is the case where they're asking us to test against a different slope than 0. So those are our new hypotheses. What we're going to do is calculate, we're going to do the same thing. What is the probability that our observed value is less than, our observed slope is less than negative 0.345? Isn't that still the slope we observed? We still observed that slope in our data. But now we're testing it against this. So now when we go to calculate the test statistic, T is less than B. What was our observed slope?
0.345.
Negative 0.345 minus our hypothesized slope, which is actually negative 1/3. So subtract a negative 1/3 and then divide it by the standard error of our observations, which is the same. Yep. So the only difference is we're instead of putting 0 in for the hypothesized value, we're putting the old value. Old research says this. So now we're going to recalculate our test statistics. So negative 0.345, it'll end up being plus 1 divided by 3, and then divide that by 0.06008, and we get that our test statistic, t is less than negative 0.194. Now, what are we going to have to do with this less than value that we're using because of our alternative hypothesis?
Multiply it by 2.
We're going to have to multiply it times 2 at the very, very end. So I'm going to do my 2 times, I'm going to do my TCDF again. Lower bound is negative infinity. Upper bound is negative 1.94, and we still have the same degrees of freedom of 10. So we got our p-value of 0.85, which is greater than any level of alpha, so what are we going to do?
Failed.
Fail to reject the null. And what does that actually mean?
That. Oh, so then it is.
You can
It's
prove
the
that.
same.
Remember the question? Here's the question. Does this new study disagree with previous research? It does disagree?
No, it doesn't.
No, it doesn't disagree. The null was that the slope is what the old research says. So since we failed to reject that null, the new research agrees with the old. That's what it means. The new research on nest depth agrees with the old. Okay, so that's a test. Now, how do we translate that into a confidence interval? And so we've got, well, a 95% confidence interval for the true slope in the woodpecker example. So this is going back to just the original scenario here. A confidence interval, if you remember, is your point estimate or your statistic, which in our case is our slope, plus and minus our t-test statistic that we're going to get from our calculator or our t-table, times the standard deviation, the standard error of the test statistic. So S sub b. The standard deviation of the slope.
Is it the same t?
No, this is not the same t that you calculate in a test. This t comes from the t-tables in the back of your book
Oh.
with so many degrees of freedom. And so degrees of freedom here is n minus 2. So what we're trying to do is estimate the true slope of the regression line using x is outdoor temperature and y is the depth of the nest. Our best guess is negative 0.345, but because of sampling variability, this is probably incorrect. We're going to calculate a 95% t-interval for beta. Beta is our test statistic. So our conditions, we're going to assume they're satisfied now. The next day of notes will be the conditions. Our confidence interval is our observed slope plus and minus our test statistic times S sub b, just like I wrote up there, and degrees of freedom n minus 2, so the degrees of freedom here is 10. So there's our confidence interval, or there's our slope. 2.28 is going to come from doing TCDF, or sorry, inverse T. So you're going to go to second distribution, whoops. You're going to go to inverse T, and the area for a 95% is point, what? 975 with 10 degrees of freedom, and that gives you your T of, that's where they get the 2.228. And then 0.06, that was the value that we had on the other page. We used it as 0.06008. They just rounded it. So then we calculate, this is our confidence interval. So then we say I am 95% confident that the interval from negative 0.479 centimeters to negative 0.211 centimeters captures the true slope of the regression line using x equals outdoor temperature and y is the depth of nest. So interpret the slope in the context of the problem. We actually already did that on the other page. When we said for every 1 increase in degrees Celsius, the depth of the nest goes down by 0.345 centimeters.